أنا اسمي إسلام. أنا visiting home in San Francisco. Staying in Lebanon for the summer وقابلت باسم في سامعيني at the back. طب I'll speak up. قابلت باسم من 3 أشهر تقريبا بأبو ظبي at a hackathon. وبعدين لما جيت يعني I had to grab coffee with him وقلت له شو رأيك إذا عملنا machine learning workshop لأن في programmers كتير حكيت معهم هون عندهم الاستعداد والحب إن هم يتعلموا هالشيء بس ما كان في فرصة إن هم يتعلموا هالشيء عن قبل. فبالنسبة لي I lived in San Francisco for 4 years تقريبا. I worked on a number of machine learning projects at a number of startups there. Maybe I'll talk about that maybe tomorrow towards the end of the workshop. But for now, we'll begin with a theoretical introduction on what machine learning is, and then we're going to dive into code. I'm a big believer that code is the best way for you to learn. So the coding will be the most of this workshop. Expect to be writing code for most of this. I'll begin covering the theoretical part, and then we'll dive into setting up the environment, setting up the coding, all of this stuff. Okay? All right. So I'll start super high level. The first question that I have to you is, what is learning? Any ideas? Sure. اسمك? زعتر. Yusuf.
It's making mistakes.
Learning is making mistakes.
And identifying the mistakes in future steps.
And identifying mistakes in future steps. Cool. Any other definitions of learning? How would you define learning? Building skills. Yes. And so I looked it up in the dictionary. This is the dictionary definition. I'm blocking it. It's the acquisition of knowledge or skills through study, experience, or being taught. So let me give you an example, like reading. Is that something that you learn?
Of course.
Yes. Okay. So what about growing your nails or growing your hair?
No.
Why?
You don't have control over it. It's indolent.
Yeah. And so there's a very important distinction that I want to make between something being programmed versus something being learned. So for example, if you look at humans, there are some things that are already programmed. These are things that are in your genes. So for example, growing your hair, breathing, blood flow, repairing your wounds, digesting food, and so on. All of these things are encoded in your genes. And so you didn't learn them because you were programmed with it. And then there's all these other things that you learned after you were born. So reading, writing, language, driving a car, writing code, going to the gym, all of this stuff are things that you learned. So it's things that you acquire through experience. Okay, so given that, let's look a little bit closer into how humans actually learn. So this is a baby learning to read. And if you think back, maybe when you're 3 or 4, when you're introduced to reading, you're learning by example. So you would see, oh, this is an A, this is a B, this is a C. You would see thousands and thousands and thousands of examples over time. And then your brain is able to generalize it. You're able to see that all these different variations are A, even though you've never seen those before. Like, I can tell that this is an A, the crocodile with the bird inside. I can tell that this is an A. I may have never seen this font before, that this is an A, that the A with the 2 eyeballs on top is an A. I'm able to identify all of these things because your brain is very, very powerful at seeing the different patterns, the general pattern of an A, and seeing it everywhere else. And so if I come back to machines, what is machine learning? It's actually the exact same thing. It's the acquisition of knowledge or skills through study or experience by a machine. There really is no difference between humans and machines as far as learning goes. The exact same rules apply. One extra definition that would be helpful for you is the ability for machines to learn without being explicitly taught. This actually doesn't apply just to computers. It applies to humans as well. As we mentioned, some things in you are programmed in your genes, and everything else is learned. Okay, so we talked about how humans learn, the difference between programmed and versus learned. what machine learning is at a super high level. But why should we care? Like, why does it matter? Why should machine learning exist? Why should we even bother with this? Well, it turns out that there's a lot of problems where it's very difficult to program, but it's actually much easier to learn. For example, what is this? It's a tree. You had no problem in identifying that this is a tree. Okay, but how would you define a tree? Let's see if we can program this.
It's a fractal.
It's a fracture.
Fractal.
A fractor.
Fractal.
Oh, a fractal. Okay. Any other definitions of a tree?
Branches and leaves.
Branches and leaves. Well, what is a branch?
Exactly.
Yes.
The loop almost
Yeah.
never ends. Huh?
Sure. But what is a branch? Can you define a branch?
I don't know. It's a brown stick. It's a brown pipe.
Okay, it's a brown pipe. Well, what about this one? Is this not a branch?
It is.
But it's not brown.
It's an
Yeah.
illustration of a branch. It's not a branch.
Well, then it gets a bit philosophical. This is where it gets like really complicated. So if I say, it's a, so it does have a pattern, but some of them don't grow like this. Some of them are more pointy and shorter. For example, if you said, okay, maybe it's like a brown trunk with leaves, this wouldn't be a tree, and this would be a tree, but it's actually not. And you can clearly tell that this is not. And so there's so many different problems like this where it's very, very difficult to actually identify or define the problem. But you as a human don't have a problem in learning it, but it's extremely difficult to define. And it turns out that looking into the brain, your brain is actually a supercomputer. It is able to, the way it's able to easily identify these things is through billions and billions of neurons that is in your brain. For example, the part that is responsible for seeing in your brain, the primary visual cortex, that alone has 140 million neurons and tens of billions of connections. And so all these different connections are somehow able to see, to tell that this is a tree and this is an A and this is a human and this is a building. And this is just one layer of 6 different layers that are inside your brain. Your brain is a supercomputer. And so if we dig inside a little bit, your brain is hackable. For example, if you look closely at this picture, your brain will get confused sometimes because you'll see that this is a spiral, but this is actually 4 perfect circles. So your brain is used to specific things, but at the same time, it is not perfect. You can hack it just like you can hack a machine as well. So what is inside the brain? Now that is largely unknown, but what we know so far is that a brain has these building blocks called neurons, and these neurons have a state. They can either be on or off, and these neurons are connected to other neurons with connections called synapses. So these connections are used to transfer information from one neuron to the next, and a neuron can turn off or on neighboring neurons. And so at any given point in time, there's a configuration in your head of neurons that are turned on and are turned off, and these somehow map to the thoughts and whatever things that you see and hear and touch. But how that fully works remains not fully understood. But it seems like the more neurons that we have, the more neurons and synapses that one would have, the more computing power and the more intellect that you can have. So let's look at different brains out in the nature. So this is a sponge. How many neurons does a sponge have in its brain? Any guesses?
Sponge, 0?
0, yeah, you actually got that right. A sponge has no brain. What about a jellyfish? Any guesses?
Same thing.
No, she does have a brain. It has a brain. A couple of million. Actually, it's a lot less than that. It's 5,600 neurons. So it's a super, super small brain. What about a cockroach?
1 million.
No, you're good at this. It's exactly 1 million neurons. Okay, what about a mouse? I can't. A billion? It's 71 million, close. 71 million neurons and about 1 trillion synapses. What about a pigeon?
Above a billion.
2 orders of magnitude, so like...
That was 100 million, now we're talking 10 million?
It's a little less. It's a little less. Yes. So it's 310 million neurons for the pigeon. This is a cat, it's not a pigeon. Okay, how many? Yes. Okay, so a cat, let's see, a cat has 760 million and around 10 trillion synapses. Gorilla, any guesses?
1 billion.
1 billion, it's more, it's way more. It's more than 10 billion. It is 33 billion actually, close. Okay, and then humans. Less than. Yes, let's not get into that. Okay.
I think it's 15 trillion.
No, it's less. Close. So we're actually at around 86 billion neurons and around 150 trillion synapses. Now, are humans, so actually the baby has less neurons, but at an adult it's about 86 billion. Now, there are creatures that have larger brains, but it's not clear why they're not necessarily more intelligent. This is why I'm saying it's still largely unexplored, but we can see that there's generally a correlation between the more neurons and synapses you have with more computational power that's in the brain.
Are dolphins having more neurons?
So one type of dolphin has a significantly larger brain.
Is it the one that uses echo?
I'm not sure. It might.
Beluga.
Yes, but for example, there are types of elephants and dolphins that have 3 times as many neurons as humans, but there are different theories of why it's not more intelligent. One theory is where the neurons are in the brain matters. So the part that really matters for abstract thought is called the cerebral cortex. In humans, they have around 16 billion neurons. For elephants that have much larger brain, they have 6 billion neurons, so it's a much smaller cerebral cortex. But all these are conjectures. They're not proven yet. Okay, so we talked a little bit of theory about there's this something called the brain, and there's these things called neurons and synapses that somehow are able to recognize patterns and identify trees and see things just like we humans do. Now, it's time to actually take this into some code. So we're actually going to write, or we're going to see how we can use a brain. This is going to be very analogous to the brain in nature. And so the first thing I'm going to do, we're going to get you set up shortly, but I want to actually demonstrate the code first so that you can see how this all fits together. Now, this is going to closely map to the example of human learning that we talked about before. So in a human, you see a human reading the alphabet, you see thousands and thousands of examples of characters, and then from that you infer the general structure of what an A looks like, what a B looks like, and so forth. So if you want to do this with a machine, is it okay if I am recording the screen. I got you. And so if we want to do this with humans, can you hear me, guys, at the back? A little bit, okay. So if we want to do the same thing with humans, the first thing we have to do is to get a data set. A data set is going to be a data file that contains all the different examples of whatever it is that we want to teach. So in this example, we're actually going to teach a brain to understand digits. It's going to be able to recognize a picture. You're going to give it a picture of a number, and it's going to tell you what this number is. So the first thing is we would get the data set, and I already have it downloaded. I'll get into the details of how you can do this on your machine in a second. And the second thing we're going to do is I'm just going to load a bunch of libraries that I'll also get into and more individually. But the first thing I'm going to do is load the digits. And it's loading. An asterisk here means that it's running. OK, so it has finished running. And if I look at this, this is 60,000 images, and the image sizes are 28 by 28. So let's take a look at what's inside this data set. So here is an example of some of the images that we have. So this is a data set of Arabic digits, and each one has a label. So this image of the number 3, has the label 3. This has a 4, 5s, and so forth. And notice how deceivingly complicated this problem is, or deceivingly simple. It's actually quite a complicated problem. Look at the difference between this 5 and this 5. You don't have a problem in identifying that both of these are 5s, but they're actually written very differently. And as an image, it looks very different. OK, so we took a look at this data set. And now the next thing we're going to do is, this is what the image, you wouldn't be able to see it well here. Let me see if I zoom out. Yeah, so this is the matrix of what each image looks like. This is what the brain actually sees. So this is a 28 by 28 image, and each number here is the pixel value of that image. If you look closely, you can almost see the number 9 in this. This is what the brain is actually processing. Okay, and so the next thing we're going to do is actually going to teach the brain. So in this case, we have 60,000 images, as I mentioned. And now we're going to create a brain, and then we're going to make this brain learn. We're going to give it the images and the labels with that image. And so what is actually happening now? This is the brain as it's learning in the background. The two things that I want you to pay attention to are the accuracy. I don't know if, can you guys see this number? Yes, so this is at 96%. So right now it's saying that based on what it has, based on the study and the learning that it has done so far, it has gotten 96% of it correctly. And as you go by, you'll notice that this accuracy is getting better and better and better over time. So how does this work inside? This is what we're going to be discussing in the next day, tomorrow. But for the purpose of today, I actually want you to learn how to use this. So the next thing is now once this brain has learned, let's actually see if it has learned well. We're going to test it. And so I'm going to load some images. And these images, the brain has never seen before. So I just loaded it. And let's look at one of these images. So here, I just loaded test image number 18. And so this is the image that we have. Now let's run it by the brain and see what it will give us. So here I would do a brain.predict, and I give it the image. And then look at the prediction. And in this case, it tells me that it is an 8. So I was able to identify that this is an image. Now, let me get, instead of just predicting one image, I'm going to predict all the images. So here, predicted 10,000 images. And here are the predictions. And now let's actually get a sense of like where this brain is going wrong. Let's see which ones we messed up, we didn't get correctly. So here I'm figuring out which ones are incorrect. And then I'm going to take a look. Okay, so these are some of the things that got wrong. And you'll notice that some of these things are genuinely hard. For example, this was actually a 0. I thought it was a 5. It actually looks like a 5, but whomever wrote it meant to write a 0. Let's see. This was also a 5, but it predicted it to be a 0 because it was more like a big dot. This was actually a 3, but for whatever reason it predicted a 0, I guess because it was very, very clustered. This one, it predicted it to be a 0 because when you look at it closely, it's more like a dot, like the Arabic 0. So looking at this gives you a sense of, okay, what is it that the brain is having trouble with? And these look like it's genuinely hard. Like I have no idea what this is, but it says it's an 8, whomever wrote it. Actually, it is an 8 now that you tell me what it is. So this was a sanity check to see that the brain is actually working properly, and it's almost comparable to human performance. Like some of these things I would struggle in identifying as numbers. Okay, so the first thing that we want to do now I showed you how you can, or a very simple example of a brain learning Arabic digits. We're going to do two things. One is we're going to set up the environment. Yes, right, and we'll make it work, and actually run this code. And this next thing is we're going to move on to an exercise where instead of us teaching it Arabic digits, we're going to be teaching it English digits. And to give you some...
Sorry, Sam.
Sure.
Sorry. Third one, bottom row.
Third one, this one or this one?
The actual was 0.
This one?
Yes.
So the actual was 0, and the predicted was an 8.
I
So,
would see that as
yeah, that looks like an 8 to me,
Yeah.
too. But whomever wrote it with the intention of it being a 0.
Okay, but the machine actually
Yeah,
predicted
so,
the right answer.
so in this particular case, I think because it was a dot, like the person put in a dot and then it smudged a little bit, and then it ended up looking like an 8. So in a typical scenario, you as a human would mistake it for an 8. I mistake it for an 8. And so this is where machines and humans sort of become comparable. Learning is not perfect in this case, but as long as we see that the things it got wrong are things that are genuinely hard, then this is a sign that it learned well. Any other questions about this so far?
Are we considering it to be scaled up? So, for example, first up row on the left,
Mhm.
it's a match with 0, so it could be a dot, but he circled it, so
This is a 5.
Yeah, so the actual is a 5, and then it thought it was a 0 because it was very like round. And
I meant to say that the data set are considered to be of the same size, or some of them are enlarged.
no, they were all.
Why that could be one?
Yeah, that's a good question. So I'm not sure how this data set was particularly prepared. My guess is it wasn't. My guess is the 0 was scaled a little bit, and maybe that was part of the problem. Like if you look at some of the zeros, they're actually quite big, very large dots. Okay. Any other questions about this so far? Okay, so if you have gotten the repository for this workshop, I think you should do a git pull because I've made some last-minute changes. But the repository will have the brain that we're going to be using to learn. It'll have this file that you'll be able to run. And what I'm running here, you may have asked, what is this thing that I'm running into? This is called a Jupyter notebook. Think of a Jupyter notebook as a place where I can write text, or I can have a notebook, but at the same time, I can have code that executes. So whenever I go to a code block, I can write like Shift Enter, and then it executes that code. Like when I rerun this, it's going to get another random sample and show it. So this is an easier way for you to test things out and for me to pinpoint some of the codes, and then I can rerun different lines of the code as well. Okay, so I want to get started on get the repository, and then what you're going to do, if you have everything set up, what you should be doing is you're going to go to the root package of your repository, and then you're going to type, I'll make this bigger, Jupyter Notebook. And what this is going to do is it's going to open up this notebook interface that we have, and then you can open up Arabic digits, and then you can just click on play, and that's going to run the code, and then you'll get to see it in action. Okay, so shall we do this? Okay, no one's excited, guys. Okay, yes, the command would be, yes, so this should be their command. Okay, here. So if you have had things set up, this command should work. Hey, yeah, this one. Cool. Okay. We'll get started. Did everyone set up their environment from yesterday? Is anyone still having problems?
No.
Okay, perfect, perfect. So hopefully today will go a lot smoother. So I'm going to begin with a recap of some of the theory that we talked about yesterday. So one thing that we talked about yesterday was how humans learn versus how machines learn. And so if you look at a comparison in humans, you start by observing the world. In the example that we used, a child learning how to read, you see the different letters, be it in school, when you're walking on the street, and so forth. And then your brain is able to capture what the general pattern of each of these letters look like. In the machine, it's almost exactly the same thing. But because a machine usually isn't wandering around the world looking at it, you give it a data set. So we load a data set, and then we build a brain, because a machine doesn't have a brain, and then we teach it so that it can identify the general pattern. So yesterday we walked through an example of a brain learning Arabic digits, and there was an exercise of trying to teach it to learn English digits. So I realized I skimmed through the code yesterday a little too quickly, so I'm going to go walk through that code again, and then we're going to move forward to how this brain actually works under the hood, okay? So the first thing I'm going to do, I'm going to get into my terminal. Now this is the directory of the repository that I have. And then what I'm going to do is I'm going to run this thing called Jupyter. Now think of Jupyter as a place for you to write notebooks. It's like Notepad, but the difference is that I can put blocks of code inside this notebook, and I can execute blocks of code inside this notebook. So I'm going to open up Arabic digits. And if you remember what we mentioned before, the first thing that we would do is we would get a data set so that the machine would know what it is that we want to teach. So there was a data set that we gave the link to, which hopefully you've all downloaded. And then what I'm going to do is I'm going to take this data set, and then you see in the repository, there's a folder here called datasets. And then there's another folder called Arabic digits. And then you're supposed to paste all the files that are in the zip file into this folder. So that way the code that we have will be able to know where to read the files. Okay, so let's have a look at these files. Like, what is inside these CSV files? Are you guys all familiar with what a CSV file is? Okay, so let's look at train images. So here you can see this is a file that has 60,000 rows. And each row has comma-separated values. It actually has 784 values, and it's corresponding to the 784 pixels in the image. So it's the pixel intensity of each value in that image. And so what we do is, when we go to Jupyter, first we import some libraries that we'll be using throughout. And I'm getting an error of some sort. Let me see. Oh, I did not actually go into my environment. So I need to do, on Mac, it would be source, activate the name of the environment, ML Workshop. If you're on Windows, it's just activate ML Workshop. Okay, and you can see that it actually got in the environment, because you should see it, the name of the environment right here. Okay, now I'm going to rerun Jupyter. Close this. Okay, reopen Arabic digits. Let's re-import all this stuff. Okay, so now it has worked. And now we're going to load the Arabic digits. So this is opening the CSV file, and then it's putting all of these images in memory. Now, what do these things look like in memory? Let's take a look. So the way for you to take a look at this, you can see the shape of the data by just typing the name of the variable, .shape. And you see here, just like the file we opened, it has 60,000 images, and each one is 28 by 28. And so here is a sample image. And we saw this before. Actually, let's put it in a different one. So this is the matrix. It's a two-dimensional matrix of the numbers in an image. You can almost see the number 9 here, exactly. And the label, the corresponding label, should just be the number 9. Okay, now once you load the data set, if it's pictures, it's always a good idea to visualize things throughout. I don't think people that are doing machine learning are visualizing things as much as they should. And so this is a little function that I gave you. You give it the images and the labels, and it will pick some random images to show you. So you can get a feel of this data set. And so here, as we mentioned before, these are the 28 by 28 images, and just above them is the corresponding label. So 7, 7, 1. And you can notice the different variations, like between the 6 and the 6 and the 2 7s. This is the general pattern that this brain is meant to understand. And if I rerun this again, you should get a different sample. So feel free when you're going through the code to check that out. Okay, so now we've loaded the data set. And now, because a machine doesn't have a brain, we're going to create this little object that I call brain. What is it? That's something that we're going to talk about shortly. But for now, it is a brain. So we made a brain, and then we're going to make it learn. We're going to give it images and the labels. And so now it started learning. And you'll see we had 60,000 images. We put 48,000 images to train on, and 12,000 images, what is called validation. So here we've split the data into 80%, 48,000 images for training, for the brain to look at and to recognize the pattern in. And then the other 20%, the 12,000 images, this is used to test, to see how good this brain is. And so as the brain is learning, it's actually learning the training examples, and you'll see here is the accuracy. You're starting at 96%, and the more you learn, the better it gets. So here you end up at 99.3%, but the number that actually matters more is the validation accuracy. So this is the 20% of the data set that the brain didn't look at. And so here it varies between 97% and 98.5%. So this is actually looking pretty good. And to see further, okay, what is it that this brain, how is this brain performing? There is another data set that the brain never looked at. This is always a good idea to actually test the true performance of that brain. So we're going to load that data set. And again, always a good idea to visualize. I'm going to plot the image, or one of the images. So this is one of the images that I have. And now I'm going to ask to the brain, this was images test 18. I'm going to ask the brain, give me a prediction. What do you think this is? And when I look at the value of that prediction, it is an 8. So it has correctly identified it as an 8. So in this case, this was performing about like 98%, so it's already doing really well. But let's look at what is it that it's not doing so well. So the first thing I'm going to do is, instead of just predicting that one image, I'm going to predict all the images that are in that data set. And to figure out how many images are in that data set, I can just do images test dot what? Do people remember? Dot shape. We use that shape because this is multi-dimensional. This is not just an array, it's multi-dimensional. So here we have 10,000 images, 28 by 28. Okay, so we're going to pass in the images test. Notice we didn't pass the labels, just the images. And then it's going to give us its predictions. And then here, this is shorthand to say, tell us the indices where the labels that we had didn't match the predictions. And so we're going to run that code. And actually, let's see how many we got wrong. So here I can do incorrect dot. Sorry? So we're going to visualize in a second, but here I'm just getting a sense of how many they are. So here we got 285 images that were incorrect. Okay, so let's visualize what is actually happening. Okay, let's see. So if we look at this one, the actual one, if we look at this one, the actual was a 5, but it thought it was a 9. And this seems like a reasonable thing to do because the 5 here, it has this like squiggle, so it almost looks like a 9. This seems like a reasonable thing to do. If you look at this one, the actual was a 3, but it thought it was a 2 because they were close enough, like the edges weren't really there. This one doesn't look like a 4 at all, but it's supposed to be a 4. So it seems, this is when you tell, if you see results like this, the model is actually doing pretty well because some of these things are genuinely hard. But if you look at this and say like, okay, this seems really easy, then it means like you should be worried. Something could be not right with your model. So yeah.
If we rerun the training data
So if you look at, it's possible. So more training in most cases shouldn't hurt, but it's not necessarily going to get better. Like he'll realize.
Today's output is worse than last night. If you,
Oh, let's see.
if
Let's
you
see.
notice the first row,
Mm-hmm.
the last two to the right.
Yeah.
first row,
This
both
one?
are ones.
Mm-hmm.
I predicted them as zeros.
That is true. Let's see. Well, let's look at another one. Let's look at another sample.
I got 169.
169? Yeah, so he has a better brain because it happened that his brain learned better in this case. Okay, well, in these examples, it's actually, these seem plausible, like that one that it's at the very top right, it's way too tilted. The 4 is also way too squiggled. The 7 is like way too thick. This seems reasonable, but yes, probably more training would solve this problem. That makes sense. Okay, so this was some of the things that we talked about yesterday. And an exercise, which I was hoping to get to yesterday, but didn't because the setup took a little bit while, is now with the knowledge that we know here, can we teach that same brain, no changes, to learn English digits? And so the exercise, actually, let me just figure on this. If I go to exercise 1, you'll find this in your repository as well. So this data set, let me just close this thing. So this data set is hosted on a website called Kaggle. And this is actually a competition. So this is a competition, or Kaggle is a website for hosting machine learning competitions. So if you go to Kaggle, you'll actually find dozens and dozens of really cool competitions, and some of them have prize money of like $100,000 if you get the best machine learning model for it. So some of the competitions you'll see is identifying whether or not there's a tumor in an image, or trying to give in an image with a car to figure out where the car is and strip it out of the image. Very interesting stuff. So if you have the time, check that out. So one of the competitions that they have for starters is the digit recognizer image. So this is a data set with English digits. So we're going to download that data set. And then we're going to do a very similar thing to what we did before. We're going to load the data set. And what was the one tip I mentioned about working with data sets? Something that a lot of people don't do when working with images. Visualizing, yes. So here I put it to visualize. So let's go ahead and do that. So visualize.show sample. And here I'm going to pass it the images as well as the labels. Okay. So it looks pretty similar to the other data set that we had, except it's in English. Okay, and now we're going to build the brain. And all we had to do for this exercise was we're going to use the brain object that we had before. So I'm going to go ahead and create a new object, brain. And then I'm going to make that brain learn from the images. Cool, so it's starting to learn exactly the same process as we had before. So here, it split the data set, 80% of it went into training, the other 20% it's using for validation. And notice at the beginning here, it had a bit of a poor start, it was at 92%, and then over time, it has bumped up to 98%, 98, and here 95, all the way to 97. So comparable performance. This is the same brain, we didn't change anything about it. Just like a human brain, one brain speaks Arabic, another speaks Hindi or whatever language that is. Okay, so let's test it out. So I'm going to load some test images. And also, what's the tip that I asked for 30 seconds ago? We're going to visualize again. Always visualize. Show sample. I'm going to give it some of the images test. Okay, so they look pretty similar. This one might be a bit hard to predict. And then we're actually going to ask our brain to do predictions. So I'm going to run it and ask it to predict. and then give it the test images. Okay, we're getting an error of some sort. Oh, I said I should do predict many. So predict was for a single image, predict many is for multiple images. Okay, so it has predicted all 28,000 images. Let's see what this looks like. So here this is an array of 28,000 numbers. Each one would be corresponding to the prediction of the equivalent image in the images test. Now the final thing is we actually don't have the labels for these images, meaning that I don't know how well it actually did for these images. And that's the whole point of that competition on Kaggle. You would build a brain, and then you would train it, and then they give you a test data that's unlabeled, and then you give the predictions from your brain, and then you give it to Kaggle, and it'll give you a score. So here I wrote a little function for you that is going to take these predictions, and then it's going to write a file called submission.csv. So if I go back to my repository, okay, it's right here. Notice it was just modified today. And this is what the submission file looks like. So the ID of each image, as well as the label that our brain thinks is correct. So we're going to take the CSV, and then you can go to Kaggle, submit predictions, and then here you can upload. Oh, this is going to be challenging with one hand. Let's see. You're going to upload your submission.csv. And then you click Make Submission. And now it's actually checking against the labels because it knows the correct values, and it gives you a score. Oh, and here I am. I got a 97, around 97%. Not the best, because some people got much, much higher scores, but it's still pretty good. And so if you go through that notebook, exercise 1, you'll be able to make a submission on Kaggle if you haven't done so already. Okay, cool. So that was the material that I wanted to cover yesterday. If you haven't been through that exercise, please do. And now we're actually going to get into a little bit more theory. And maybe one obvious question that you've had as I was going through this is, what is this brain thing that we've been using? And so this gets back to one thing that we talked about yesterday, the brain consisting of neurons and synapses. And what we know that in this thing, you have over 80 billion neurons that are connected with each other with trillions of connections, about 150 trillion of them, and that each neuron, it has a state. So a neuron can be active or inactive, and a neuron can transmit messages to neighboring neurons to activate them or deactivate them. So at any point in time, there's a configuration in your brain of which neurons are active and which ones are not active, and somehow this is mapped to your thoughts. And the more neurons that you have and more synapses, in theory, you should have more computational power. Okay, so let's go back to the very simple building block of what is a neuron. And here we're going to move from biology to computers. So let's start with what a neuron is in the land of computers. So a neuron is the building block that we'll be using, and you can think of it as something that takes in an input. It could be one input, could be many inputs, and it makes a decision, whatever that decision is. So let's look at an example. Let's say I want to figure out whether I should study computer science or not. So there are several factors that go into that decision. Let's say, do I think this is an interesting field? That's an important factor. Are there jobs available after I graduate? Is there a good school that's nearby and close to home? So these are all factors that would help me make that decision. And so here I'm going to take all of these factors, I'm going to put them in variables. So for the first factor, I'm going to call it x1, second factor x2, third factor x3. And I'm going to give the variable a 1 if the answer to that question is a yes. I'm going to give it a 0 if the answer is a no. So, for example, let's say I think computer science is interesting and there are jobs, but the school isn't close to home. What would be the values? I didn't hear that.
1110.
1, 1, 0. That's right. Let's try another example. There are great jobs in computer science, but there isn't a school nearby, and I don't find it that interesting. 0, 1, 0. Is this clear to everyone? Okay. So we've taken the factors that we have, and we've encoded it into variables. The next thing we're going to do is, so these are the factors we're feeding into our neuron, and the neuron is going to take these three things and make a decision. But how are we going to make that decision? Well, one way we could do it is using what we call a decision function. And this is what we're going to use. So we're going to sum up all the x's that are here. And if the value of this sum is above a certain threshold, we'll say yes. And if it's less than or equal to that threshold, we'll say no. Make sense so far?
Yeah.
Any questions? Cool. So threshold here is a bit bulky, so I'm just going to rephrase threshold to theta. Cool? Okay, so let's look at the examples that we've had before. Let's say I set the threshold to be 1. Okay, I think computer science is interesting, there are jobs, but the school isn't close to home. We've already mentioned how this is encoded. x1 is 1, x2 is 1, x3 is 0. Now based on this decision function, what should be my decision?
You should go for it.
Why?
It's 2.
Okay, yes, exactly. So I sum them all up. Exactly. So I sum them all up. It's 2, which is greater than my threshold, so I should go. Okay. Now, second example. There are good jobs in computer science. There isn't a school nearby, and I don't find it that interesting. You should not go. Yes. So in this case, it equals 1, which is less than or equal to theta, and so I wouldn't go to computer science. And you see, neuron is a very simple thing, but it's able to capture simple decision models. Okay, let's look at a more abstract example. So let's say I want to implement an OR gate. So in this case, I have two inputs, x1 and x2. So I have, whenever they're both 0, the decision is 0. And for all the other states, if any of them is 1, my decision will be 1. So now I need to find out a value of theta that would make this true. And so let's say I choose theta to be 0.5. Does this work? Well, let's see. So at 0 and 0, I'll add them all up. It's 0, which is less than 0.5. And so the decision is 0, as expected. At 0, 1, x1 plus x2 is 0 plus 1, which is 1. Also, which is greater than 0.5, greater than my threshold. And so it's yes. For 1 and 0, it's the same thing. And for 1 and 1, the sum is 2. It's greater than 0.5, so my decision is 1. And so one neuron was able to implement an OR gate. And one way to visualize this is, these are the 4 points that we've had here. The white ones are where I want the decision to be 1. The black dot is where I want it to be 0. And when I put theta to be 0.5, I'm actually drawing a line that separates the white circles from the black circles. This is the line where things equal theta. So here it's at 0.5, and here's at 0.5. Any questions so far? Make sense? Okay, let's try an AND gate. We also need to figure out a theta to make it work. Let's say we do, any guesses actually on what theta could be?
More than 1.
More than 1, that's correct. So,
0, 1.
yes, exactly. And so if we choose theta to be equals 1.5, let's look at the examples. 0, 0, less than 1.5, so the decision is 0. At 0, 1, it's less than 1.5, so a decision is 0. X1 and X2, it's also less than 1.5. 1 and 1, it's 2, which is greater than 1.5, so the decision is 1. And notice 1.5 isn't the only solution.
Yeah.
Like 1.1 could have worked, 1.2.
Between 1 and 2.
Or even more, yeah, exactly. And again, visualizing it, in the case of the end, we only want this value to be decision 1. And so we've moved the line from where it was for the OR to here, separating the white circles on one side, the black circles on the other. Okay, let's try another example. In this case, I want to implement an XOR. So an XOR, in case you don't remember, you only want the decision to be 1 when only one of the values is 1.
Different digits.
Different digits. What do you mean?
And different digits produces
How to
1.
affect
2? What do you mean different digits?
0 and 1 generates 1. 1 and 0 generates 1.
Oh yes, so
Similar digits produce 0.
yes, exactly. Like this.
Yeah.
This is correct, right? So what would a theta be that would work for this? Yeah.
Not exactly 1.
Well, so that actually won't work. That won't work. Between two values. Is that right? Yeah, I think you're actually pretty close. So if you look at this visualization, there's something different. There's something different about this than, say, the end. Notice that in the case of the end, I was able to draw a line that separates the white, where decision is 1 on one side, and the decision is 0 on the other side. And the OR was the same thing.
This one
You
you can't.
can't.
It's a curve, right?
Yes.
If it's 2, it's a dot.
Exactly. But you can't have a curve in a neuron. So a neuron, a single neuron, can't capture this. I can't do an XOR with a neuron. It's not possible. But what is possible is more than one neuron. So I'll put 2 lines, and I will say everything that's between these 2 lines is going to be a white circle, and everything outside of that is black. And so how are we going to implement this? Remember this line? This was the same OR line that we had before. So, yeah. So there's an OR. We know there's an OR. Yeah. Yes, that corresponds to an OR. And this was an AND, the AND line that we had. But the AND line is different because the AND made all the circles on this side white and this one black. We want the reverse of that. And so to do that, we'll put everything it'll be a not AND, basically. You'll reverse everything. And then you want things to be the ones that are to the right of this one and the ones to the left of this one. And so you AND these 2 results and you'll get your decision. And so if I expand this, we've built an OR, we've built an AND. So the full neural network is, remember, the one with theta 0.5, the AND, theta 1.5. For the not AND, I actually took the negative of the inputs and I put in the negative of the theta. This is how you can do a not in a neuron. And you can see, in this case, I took a very simple neuron that's capable of doing very simple decisions, and I put them together in blocks to solve something that's more complex. And so you can imagine, these are 3 neurons. If I put hundreds or thousands or millions, or in the case of your brain, billions and billions of them, it is able to do things that are much, much, much more complicated, like recognizing digits, like singing, like dancing, like driving a car, and so forth. Okay, so a couple of things that I wanted to cover. If I go back to the original example, some of these things, there's so many cases where some of these factors are more important than others. For example, maybe I think the fact that the subject is interested in me matters a lot more that there is a school close to home. And so to represent that, yes, with weights, exactly. So we're going to be introducing weights. And so every connection that you see here will be weighted. And so instead of the decision function just being the sums of the x's, it becomes the x's times the w's. So we'll be doing x1 times w1, x2 times w2, x3 times w3, and summing those all up and checking if it's greater than or equal to the threshold. Any questions so far? Cool. Okay, so let's try an example. I think computer science, that was the example we had before. We've encoded it to x1, x2, but let me add, I only care about getting a job after I graduate, and I don't care about anything else. Yeah, so what should the weights be?
0, 1, 0.
Yeah, 0, 1, 0, or 0, 10, 0. It doesn't matter what W2 is as long as it's positive. Okay. For the same example, what if I say, being interested in the subject is very important to me, and I actually want to move too, so it's better if the school is far away.
1, 0.
So if I do a 0 for the second one, it means that I don't care about jobs.
1, 0, 0.
Well, but I do care about jobs, but yeah. And so for this one, so here I actually want the opposite. So the opposite of this, I want the opposite of this. So W3 should be a negative number, and this should be a greater number than this one. It doesn't matter what the values are. So 2, 1, negative 1, 20, 10, minus 15, as long as you're having the right ratios. That's what matters. Okay. Now you might be wondering, okay, we've shown how to have a group of neurons to create decisions, sometimes more complicated decisions, but where's the learning? Like, how does this tie to actually learning things? So learning is figuring out which parameters and thresholds to use. So in the case of the digits problem that we did with Arabic and English, they are the same network of neurons. The only difference is that we chose different weights and different thresholds in the connections to make it learn Arabic versus learn English, but it's the same network structure. And so this is what learning is, and this is also what learning is inside the human brain as far as we know, or as far as I know. So in this case, we have 4 parameters. We have 3 weights and a theta. What about this one? How many parameters do we have? This was the neural network, or the group, and the group of neurons, by the way, is known as a neural network. 4? There's more. There's 9. So every connection here has a weight. 1, 2, 3, 4, 5, 6. And there are 3 thresholds to figure out as well. So it's a total of 9 parameters. And you notice here we've made a leap. We've actually changed the learning problem into an optimization problem, which is something that has been studied for a long time. And so here we want to choose the parameters, the weights and the thresholds to minimize our error. But what is the error? You can define the error in whatever way you like. So one definition for the error could be the mean squared error, which is I look at what is the correct value and what is the predicted value, and I take the square of the difference. But you can have different values. You can have different error functions as well. And you'll need an algorithm that takes this error and tweaks the weights and thresholds to minimize the error. And so there are several algorithms again to use, but one very common one is called stochastic gradient descent. This was, or as we'll demonstrate in the code shortly, this is something that we'll be using to actually optimize these weights. Now, how does this algorithm work? And the definition of this, I think that'll be too deep for this session. I would rather you to focus on the high-level code of how to use these different building blocks to build neural networks to learn things. But there are plenty of resources to look into. Maybe this is something we can do in the future if people are interested. Okay, so another thing is we said that the decision function is the summing the x's times weights. And it has the value of 1 when it's greater than a particular threshold, and 0 when it's less than a particular threshold. So it's a step function. But sometimes the decisions aren't always this binary. It's not like, I'm going to study computer science, I'm going to study computer science, and then finally I'm all in and I'll study everything that I can in computer science. It's usually like varying degrees. And so you can use different decision functions depending on how you want your neuron to behave. So for example, these are some functions that you will see when you look at code bases of machine learning. So sigmoid, ReLU, softmax. This is what a sigmoid function looks like, for example. And so it's good to use the sigmoid function in your decisions because then you'll have a degree of confidence in your decision as opposed to yes or no. So sigmoid is one of the functions that you can use as well. Okay, so we talked about neurons. We showed how neurons are grouped together to make more complex decisions. We mentioned that a group of neurons is a neural network. Now, we're going to talk about what is the neural network that we used to recognize digits in those examples. So we took an image, 28 by 28 image, 24 pixels, and this is the label that we're using. So here, this is actually a vector of 10 digits, and this is saying that the label is 7. So I'm putting 0 for everything, and I'm putting 1 for the value of 7 that I want. And I'll explain why we do this in a minute. And then the first thing we're going to do is we're going to flatten this two-dimensional matrix. We're going to make this just one long 784 by 1 vector. And then we're going to build a layer of neurons. In this case, I'm going to add 512 neurons, and I'm going to connect each one of these pixels to all 512 neurons. So the first one is connected to all 512, the second one to all 512, and so on and so forth. And then I'm going to make another layer of 512 neurons. I'm going to connect everything in this layer to this layer the same way. And then finally, I'll be doing what's called the output. So here I'll have 10 neurons, and the output of each of these neurons, they're all connected to this layer. The output of these neurons will be the probability corresponding to that particular digit being the correct digit. So in the case of 7, I expect the 7th node to have a significantly higher value than all the other ones. So why 2 layers? Why did I choose 512 neurons here? There's unfortunately no good answer to that. So there's nothing, at least so far, there's no known science where you look at a problem and you put it in a formula that tells you you should use 2 layers, 512 neurons each, and you're going to get the best output. This is actually largely unknown. So right now, people actually, they have heuristics on what would be good. Like generally adding more layers gets better learning, but it's at the cost of slower training time. But it's largely an art, and you try different stuff and eventually you see that patterns emerge, but putting that pattern into a science has yet to be done. And it is frustrating, I know. So 512 was chosen at semi-random. You can read some guidelines of some ways of designing good neural networks, but it's not a science. There is no exact reason why this is 512 and not 600. But today, when you're building your own neural networks, you should try adding more layers, try changing the number of neurons, try changing the decision functions that we used, try changing the error, and see how this impacts your performance. Okay, so we've described the general structure of the neural network that we built. Let's look at the actual code. Sure.
Is the runtime of the algorithm, so it increases with the number of neurons?
Yes.
Is this model, do you know by how much it increases, or you have no idea?
That, I don't know the exact relationship. Like I don't know if it's linear or not. But that is one thing that would be worth testing out today, for sure. But to give you a sense of the state of the art that is there today, for example, there is a very well-known competition called ImageNet, where they would have many, I think on the order of millions of images, and then you have to classify it into 1,000 different categories, like dogs and insects and plants and so forth. And the state of the art of 2013 was a model called VGG19, and so it had 19 layers like this. I don't know the exact sizes, but I'm sure it would be bigger than 512. So it's massive. And so training a network of that size would take days, and you probably want to run it on GPUs. We're going to be using the CPUs right now. And you probably want to run it across multiple machines. It gets vastly more complicated. But digits, they're simple enough that you can run it on one machine. It's fast to train, and it's a much smaller problem, so you don't need neurons of that size. Any questions? Other questions? Okay, so I'm going to jump into the code, and the machine learning library we're going to be using to do neural networks is called Keras. So you're going to start by importing Keras, and then first you're going to define, remember what we talked about in a brain? Actually, when you're writing in machine learning terminology, it's called the model. So the model is exactly what that brain was that we talked about before. And I would say it's a sequential. Sequential basically means that it's a sequence of layers. You can have a graph where different layers are linking, but for the purposes of today, it's all just a sequence of layers. So, okay, so it's a sequential. And now what am I going to do? I'm going to flatten the input. If you remember the first step that we had, we took the image, and then we flattened it into one vector. So here I'm telling it the input is 28 by 28, and I'm flattening it to be one vector. The next thing is we had a layer of 512 neurons, and so I can do that by saying dense. Dense is saying connect all the 784 values that are here to all the 512 neurons that are here. And the activation, think about that's the decision function that we were talking about. ReLU is one of the decision functions. You don't have to use it, but it is actually, the nice thing about it is that it speeds up the training. So if you try other functions, it should still work, but ReLU generally is a good practice for middle layers. I'll talk more about that in a second. And then the next one, we're going to have another layer of 512, so it's exactly the same thing. And then finally, we're going to give it the last layer of 10 neurons. Now the last layer should be corresponding to how many different types of things you're labeling. So in the case of the digits, we have 10 digits. Sorry? Yeah, exactly. 0 to 9, so we have 10 digits. And so I want 10 neurons to be my output. And here, I'm choosing softmax as my decision. The reason we're choosing softmax as opposed to something else is that we want the outputs of these 10 neurons to be a probability. So as when you use a softmax, this makes sure that all the sum of these neurons sums up to 1. And so when you look at the output, you can interpret that as the probability for that neuron to be equivalent to that corresponding digit. So this is the neural network that we have. And then finally, this is, now that we've outlined the architecture, you want to tell it how do you measure error and what algorithm that you want to use to minimize the error. And that's what we're going to do. We're going to use the mean squared error, as we talked about before, and the algorithm, or the optimizer, is stochastic gradient descent. And then you can optionally add another, so if you just leave it at that, then when you're learning, it's only going to show you the error, which sometimes it's not as easy to understand. If you add accuracy to your metrics, it'll show you the percentage of images that it got right, and which ones it got wrong. So this is an extra to see. And you can look up, Keras has really good documentation, so you can look into what is dense, how it works, what are the different activation functions that you can use, what are the different loss, what are the different optimizers that you can use. You can try all these different configurations on various data sets that are out there, on Kaggle or otherwise, and explore how that actually changes things. You can add more layers. There's a lot of things that you can play with here. So if I put this code in the English digits, it should work. If I go back. I'm just going to copy this. I'm going to go here. I'm going to restart the kernel. Okay, so this was the English data set that we had before. Let's just double check that this is the one. Oh, I didn't load the data set. Okay, and here, I'm just going to paste in that code. So here I've made my model. And this is actually code that I didn't talk about. And I'm considering leaving it for you to figure out what it is, because otherwise the exercise will be way too easy. But think of this code block as it's the equivalent of actually making it learn. And so now it's learning. And here, I used actually different error and optimizers in the brain Python file. So this one actually is training because I used different algorithm. This algorithm is actually a little slower. So you'll see it's starting at 20% as opposed to the 96% that we had before, but it's slow, it's catching up slowly. So here it's at 78%. Now it's getting to 85. And if we give it enough time, it'll get to similar levels that we've had before. Okay, so now we're going to move on to exercise 2. And in this exercise, there is another data set on Kaggle, if the internet is cooperating. This is a data set of Arabic characters. So what you're going to do is you're going to go to that link. You should have all downloaded this data set. Did anyone not get it? We have it locally here if people need it. Okay, cool. So we're going to get this data set, and then again, you're going to go into your datasets folder. You're going to go to Arabic characters, and you're going to dump the files here. And we're going to do what we've done before. Let's see the characters. So this is very similar to the image problem, except instead of having 10 digits, in this case I'll have 28 Arabic letters. And so the label that you see on top of the image, it's corresponding to the index of that letter in the Arabic alphabet. So alif is a 1, ba is a 2, ta is a 3, until you get to a 28. Okay, so in this exercise, let's not use the brain. I want you to build a model or a brain that would learn these digits using Keras. If you actually try to use the brain, it's not going to work. It will give you an error. So I want you to look into the code of the brain, and I'll also show the sample of code that I just shared. I'll keep it on the screen. Look through that notebook and try to write the Keras model that would make this learn. Now, if you look at the size of this data set, remember? Dot shape, yes. So here we have 13,440, and it's a 32 by 32 image. So the data set here is actually a lot smaller than what we've had before. And at the same time, the number of labels, in this case it's 28, it's a lot higher. So the number of examples for every label is a lot less. So you'd expect that the brain wouldn't be able to learn as well as it did with the other one because you had a lot more data for it. But try it out, see what numbers you can get. Any questions before we move on to the coding part, the fun part? Rayan.
If the output of multiple, I don't know, the final output, if two are equivalent or more than one are equivalent, exactly the same output, what will be the...
So let's look at that actually a little bit more closely. So if I go to, let's say here, Here I made a prediction of this image, and what I'm going to do instead is I'm going to use Keras directly here. Predict. I think this works. Let's see. I'll need to check the syntax. Or 18. Oh, 3 dimensions. Oh, missing. Still missing. 1 second. I'll get this. Okay, I'll need to look at the command to get to you, but the output, if you use the model.predict that I was trying to use here, and I'll figure out the syntax shortly, it actually outputs the probabilities of each of the layers, the output layers. So each of the 10, it is almost impossible for you to have 2 numbers to be exactly the same, because these numbers have very high precision, and so it's almost impossible. In which case, it takes just one of them, but that's a rare occasion. It just takes one at random. Yeah, but I'll show you that code in a second once I get the syntax. Any other questions?
So for the digits, you have an array from 0 to 10, representing the digits.
0 to 9.
We need another one for the alphabet, which is from 0 to 26.
Mm-hmm. That's right. That's right.
What's the difference between TensorFlow and Keras?
That's a very good question. So Keras is actually a wrapper on top. So typically these days, actually let me back up. Right now, the question was, what is the difference between Keras and TensorFlow? So in the early days of neural networks, everything was trained on the CPU, which is pretty much what we're doing right now. And later, as neural networks became a bigger thing, it actually requires a lot of, as we saw, there's a lot of matrices, there's a lot of vectors, there's a lot of scalar multiplication that's going on, there's a lot of matrices involved. And GPUs, thanks to the gaming industry, are remarkably good at that. So we started moving from training on the CPU to training on the GPU. TensorFlow came about to help out with the problem of, I have many GPUs and I'm training a large network, and I want to distribute the computation across multiple GPUs. Keras is actually a layer on top of TensorFlow. So it, actually let me just get a notepad. So the flow that you have, if you're using the GPU, is you have right now Keras, that's like, think of that as like the top layer. And afterwards, that can be using, that Keras as a wrapper to several libraries. So you can use TensorFlow, or you can use another equivalent library called Theano. And in turn, these libraries, what they do is they take the commands that you give them, and then they compile them into a language called CUDA. And CUDA is the language that's used for NVIDIA chips that are currently used for training large neural networks. So Keras is a higher level API than TensorFlow. It's a simpler API to use. But in the backend, you could be using TensorFlow. If you look at the notebook, here it says using Theano backend. If I can change that, so I can open up the Keras config. So here I'm choosing Theano as my backend. I can change that and put in TensorFlow. And assuming that TensorFlow is installed, if I re-import this, actually just, I'm going to restart and clear output. Now it's using TensorFlow. So I have reconfigured Keras to use TensorFlow in this case, as opposed to Theano. And another thing that you can actually configure in the JSON, you can actually, in this configuration file, you can change it from training on the CPU or in the GPU versus the CPU. Here I do not have a CUDA GPU, so this is not going to be possible. But in cases where you actually want to take this further, what I usually do is I would rent on Amazon, I would rent an instance with an NVIDIA GPU, and then I would do my training there. So I would only pay for the number of hours that I use it. It's like 90 cents an hour or something. In which case here, I would configure it to be using the GPU. And it's orders of magnitude faster. Like something that would have taken multiple hours would take less than a minute on the NVIDIA GPU that we're using. And so some of you may have configured Theano, some of you may have TensorFlow configured, and so some of you will see TensorFlow as the backend, others would see Theano as the backend, but it shouldn't change anything. Any other questions? Diane? Okay. Okay, exercise 2, everyone. Give it a try. Let me know if you're stuck or having any trouble. Off you go. You have been summoned. And okay. Okay, is anyone still working on exercise 2? Rayan and Hassan, you guys are working on exercise 2. Anyone still working on exercise 2? Okay. And so we're gonna officially wrap the workshop now, and then we can work together to make the exercises work for everyone. Just a small little comment. I want to talk about what was covered in the workshop and what we didn't cover, just for you to get a sense of the scope of the things we talked about. So there are different types of machine learning problems. The type of the machine learning problem that we were looking at is called a classification problem. In classification, you're giving an input, and then you have a certain defined set of categories, and you want to map that input to a category. So in the case of the digits, you had 10 digits. You take an image, and then you map it to one of these 10 digits. In the case of the characters, you had, in the case of Arabic, 28 characters, and you take an image and you map it to one of these 28 characters. So this is called a classification problem. So we looked at specifically image classification. An image is slightly special because in images, realize they were all the same size. All the images that we had in the data set, they were 28 by 28 or 32 by 32. Now, there are certain types of classifications where the input is not the same size. So you can't just have the first layer process the whole input. The input can be variable. For example, in the case of text or in the case of speech, this is a variable input. So that is something that we didn't talk about, and there are techniques to incorporate that into neural networks. Other types of machine learning problems is, for example, what is called regression. So instead of taking an input and giving out a specific category, you take an input and you give out a number. So for example, I want to build a brain that would predict the price of rent in Beirut based on the current prices. So this is known as a regression problem. There is no categories that you classify to. The output here is a number. There's also another class of problems that is known as reinforcement. So in this case, you're actually learning as you're going, like playing chess or playing checkers, those types of games. So we've scratched the surface of what machine learning is because we had so little time. Also, we specifically talked about neural networks. It is my belief that neural networks is probably the most powerful machine learning model or type of brain out there. Having said that, it's not the only one. There are many models like support vector machines, like naive Bayes, plenty of different models that you can use. But I think I decided to focus on neural networks because I felt it would be the most valuable to understand And I think the theory behind it and how it ties to biology is something that's very interesting as well. So this is what we covered for the workshop. I'm hoping it was helpful. I'm hoping it inspired you to dig deeper into this field. If you have any feedback for me about the workshop, also I would love to stay in touch. I'll be sending out my contact information. Would love to stay in touch. And if you run into any issues, if you want to continue working on the exercises on your own, or whatever problems that you run into in the future, or if you just want to say hi, please do. Would love to keep that in touch. And that is a wrap. And for the people that are still working on the exercise, I'll come and make sure that you get it working. Cool. تصبحوا على خير.